Hello, and welcome to this video on migrating from the DCAN module to the MCAN module. In this video, we will highlight key steps in performing some of the common CAN operations in the MCAN module to make the migration from DCAN to MCAN easier. Please use this video in conjunction with the application note titled DCAN to MCAN Migration Guide. The link for the application note is provided in the resources section below the video. What is the need for migration? Well, C2000 devices feature three types of CAN modules: ECAN, DCAN, and MCAN. None of the three CAN modules are software compatible with each other. Some C2000 devices only feature the MCAN module, as it supports both classic CAN and CAN-FD. Please refer to the device datasheet to figure out which CAN modules are present for your device. The DCAN and MCAN modules employ a completely different architecture, and hence a very different programming approach is warranted between the modules. Some of the most prominent differences between DCAN and MCAN have been highlighted in this video. This slide highlights the basic differences between the DCAN and the MCAN modules. DCAN supports the classic CAN mode, employing the same bitrate for the entire frame. In contrast, MCAN supports CAN-FD, allowing two bitrates to be employed in a frame: a slower bitrate for the nominal phase and a faster bitrate for the data phase. In terms of the communication speed, DCAN is capped at 1 Mbps, whereas MCAN is able to support up to 5 Mbps for the data phase. In terms of payload size, up to 64 bytes can be transmitted in a single CAN-FD frame compared to only 8 bytes for classic CAN. The higher payload size for CAN-FD reduces the protocol overhead and is equally beneficial in scenarios such as firmware updates. Note that it is possible to transmit the entire frame using the same slower bitrate in MCAN, only taking advantage of the higher payload capability. In DCAN, data is stored in message objects whose number is fixed at 32. In MCAN, data is stored in buffers tied to filter elements. Depending on how the filter element is configured and depending on the available memory, the number of buffers can vary. Additionally, MCAN supports timestamping. Now, let us discuss some prominent differentiating factors of MCAN. Bit timing configuration differs between classic CAN and CAN-FD. The process is relatively easier in classic CAN since the bitrate is the same for the entire frame. However, in CAN-FD, two different bitrates can be used: a slower nominal bitrate and a faster data bitrate. In the MCAN module, these two bitrates are configured by writing to the NBTP and DBTP registers respectively during the module initialization. Note that an application can choose to only take advantage of the higher number of data bytes per frame that can be transmitted in CAN-FD and use the same bitrate for the entire frame. The faster bitrate for the data phase also warrants transmitter delay compensation, without which bit errors can occur. After configuring the bitrate, the most important task is to configure the message RAM. This step determines how the messages to be transmitted and received are stored in the module's RAM. The layout of DCAN's message RAM is fixed and supports up to 32 message objects. Every message object has the same structure, as can be seen below, and can be configured for transmit or receive operation. This slide shows the different types of data storage elements in the MCAN module. Note that this is the maximum configuration. Depending on the amount of RAM available in a specific device and depending on the needs of the application, the number of elements in each category can be tweaked. For certain applications, there may not even be a need for a particular category. Refer to the device datasheet for the message RAM size for your device. For more details on the exact structure of each section, please refer to the MCAN chapter in the device technical reference manual. The design of MCAN message RAM offers tremendous flexibility, enabling allocation of the available memory to each of the sections based on the application needs. Message RAM configuration involves configuring the following: starting address for each section. This allows the possibility to allocate the sections in any desirable order within the message RAM. Size of each section can be configured as per the application needs, although the upper limit is defined by the module. Size of certain sections can even be configured to 0 if the application has no requirement for it. The freed up RAM space can be used for other sections instead. Size of elements. This is determined by the frame data size and can be independently set for each section. However, the size in any single section remains constant throughout. Note that this setting is limited to the TX and RX buffers and the RX FIFOs only, as the other data storage elements have fixed sizes. Note that MCAN module does not check for memory overlap between sections. It is your responsibility to ensure that the sections don't overlap each other. Message RAM is addressed in 32-bit words. Therefore, the length of each section is a multiple of 32 bits. Since message RAM is configurable according to the application needs, the RAM is used more optimally. This advantage comes with the requirement for correct configuration. This step is not needed in DCAN since its message RAM is not configurable. Along with each of the MCAN examples present in C2000ware, a bunch of macros have been defined as seen below. These can be used to configure the starting addresses for each of the sections in the message RAM. Based on the application requirements, you can specify the number of elements as well as the size of the elements for the relevant sections. Correspondingly, the macro calculates a permissible set of starting address values, and these defines can be used for message RAM configuration. Note that there are multiple possible ways of message RAM configuration for successful operation. The modules also differ in the way that the received CAN frames are assessed. In the case of DCAN, the acceptance filtering for received data frames is done in an ascending order of message objects. On obtaining the first match, the received frame is stored in and can be read out from the corresponding message object. In the case of MCAN, there are defined structures called filter elements. Filter elements need to be configured in the message RAM with fields for filter type, which determine what frames are to be stored, as well as filter configuration, which determine where these frames are to be stored within the message RAM. There are two types of filter elements, namely standard filter elements and extended filter elements for standard ID frames and extended ID frames respectively. Apart from the kind of frames, both type of filter elements function very similarly. In MCAN, for each valid frame received, if the frame has an 11-bit standard identifier, it is sequentially checked with the standard filter list until a matching filter element is obtained. In case of a 29-bit extended identifier, the extended filter list is referred to. Based on the matching filter element configuration that is done at the time of module initialization, the frame can either be rejected or accepted and stored in either an RX buffer element or in one of the RX FIFOs. Another key difference between the modules is in the process of FIFO handling. In DCAN, multiple receive message objects can be concatenated to form a FIFO buffer. This is done by programming identical identifiers for all message objects in the FIFO. EOB bit needs to be set only for the last message object of the FIFO buffer, leaving it as 0 for all other message objects. The process of reading from a FIFO is exactly the same as reading from a single receive message object. MCAN offers a number of FIFOs that are separate defined structures that can be stored in the message RAM. This arrangement offers more flexibility and ease of use in various kinds of applications. There are two RX FIFOs, and as discussed earlier, filter elements can be configured to store the matching received frame in either of the two FIFOs. TX FIFOs can be utilized to store frames to be transmitted in the desired order by the application. This is relevant because for multiple messages in the TX buffer, frames are sent in the ascending order of their message identifier. TX event FIFOs can be used to store information related to the transmitted frames, including timestamps. The advantage of having it as a separate structure not only allows the module to check the order in which the frames are transmitted, but also allows the TX buffers to be populated with the next frame earlier, thus improving efficiency. Each FIFO has a corresponding register to store status information, including fill level, put index, and get index. These fields are automatically generated by the module and play a crucial role in the functioning of the FIFO. The key difference in FIFO handling is the manner in which the messages are stored in and read from the FIFO. To determine where the received message is to be stored in DCAN, like any other message, the message objects are sequentially checked in ascending order and the message is stored in the first available matching message object. In MCAN, When the matching filter element is configured to store the message in Rx FIFO, the location within the FIFO is determined by the put index. Based on this index, the module calculates the exact address within the message RAM for the message to be stored. Similarly, if at any moment multiple messages are stored in the FIFO, they need to be read in the order in which they were received. For DCAN, the application needs to carry out the processing to track where the message needs to be read from. In MCAN, the module maintains the record for the received messages in the form of the get index. This index can be used to calculate the exact address within the message RAM for the message to be read from. Thus, the additional hardware support in MCAN enhances the FIFO functionality by offloading processing tasks and freeing up the application. Note that similar hardware support is present for other types of FIFOs in MCAN as well. These are some of the major differences that you need to take into consideration for migrating from DCAN to MCAN. For additional resources, please refer to the links provided in the resource section below this video. Specifically, refer to the DCAN to MCAN migration guide application note for a detailed description of some of the aspects discussed in this video. In case of queries, you can check out the E2E forum for previously answered questions, or you can post your question to be answered by a TI engineer. Thank you.